Okay, so let us talk about energy-efficient AI. First of all, let us reaffirm the fact that hardware is important, and it does have a problem, and especially AI hardware has a problem, as we can see from this particular headline from one of the Nature journals back in 2018. Of course, since then, things haven't got any better. As you can see from this headline, ChatGPT burns millions every day, and that is on top the well over 100 million that Sam Altman was quoted as having costed to train it. So we're talking big money and a lot of energy. To that, we add this report from the International Energy Agency. Data centers and data transmission networks are responsible for nearly 1% of energy-related greenhouse gas emissions, the stuff that comes out of power plants, segue from the previous talk. And I added this perhaps more esoteric headline from another source where it says that rising energy costs, very topical, erodes the competitive edge of data center operators. This means it does impact bottom lines in a very real way. And as usual, wherever a bottom line is impacted, there's usually the potential for innovation. In this particular case, we see that more than half of the British participants in the survey talk about 10 to 30% of their operational expenses down to energy, and a quarter of them saying substantially more without disclosing further numbers. And if we just take a bird's eye view and look what's been happening over the last few years, the numbers are, well, staggering, I could say. Whether you look at internet users, internet traffic, data center workloads, we are talking about an absolutely insatiable appetite for data processing. And if you're scared of heights, don't look at what's happening with crypto. So, going on towards AI, we can see two nice pictures here. The one on the left is the data scientist's view. This, many of you will recognize as the artificial neuron that we all know and love. We have the inputs at the left. We have the weights. These are pairwise multiplied to give you the products, and then those are bunched together inside the sum of the neuron in the multiply accumulate, as we call them in computer engineering. We slap on an activation function on top of them, and presto, you've got your computation. Put millions of these things and billions of those things, or indeed hundreds of billions in some of the biggest large language models like ChatGPT, and you can achieve amazing things. Of course, there's an entire field about how to make smaller networks do more work, but what I want to talk about more is the picture on the right, which is a simplified analogy of what the hardware engineer sees when talking about AI. You can think of the battery as a tank of water, well, charge in reality, but let's take the hydraulic analogy. You distribute this strategically into different buckets. Those are your load capacitances. And then you do your computation, and when you're done, you dump the water, and that's how you dissipate the energy. So getting hardware to operate more efficiently, there are many ways you can do across the innovation stack, from better devices all the way to better architectures. And I'm just going to give one example about one of the things we do in my own group about efficiency. The basic idea is that instead of dumping the water, we put an oscillatory system whereby much of this is returned back to the power source. But let's look at it in a video. We've got graphics, and we are not afraid to use them.
Artificial intelligence is changing the way we perform computation and revolutionizing how machines interact with the world. However, more AI means more power consumption, with data centers alone already consuming about 2% of the world's electricity and growing fast. Running electronic circuits is like controlling a group of buckets that fill and empty with water. The water going into the buckets represents charge, and the amount of water they lose represents power consumption. For decades, we have been shrinking the buckets and making more of them. But smaller buckets are harder to make, less reliable, and more expensive. What if we could reuse the spilt water, making it flow back and forth? This is what we call charge recovery computing. It's part of adiabatic computing. Notably, charge recovery can work with small buckets as well as large ones. Naturally, there will always be some energy loss due to resistance, but by using this recovery mechanism, we can be much more efficient. And we can further reduce losses by lowering the system temperature. Until now, charge recovery has been too cumbersome for standard electronic circuits. But the structure of neural networks that underpin AI makes it viable. Project ACAN seeks to build the first adiabatic neural network demonstrator chip. It could lead to smaller batteries and longer usage times, more efficient data centers, autonomous vehicles, and electronic devices of all kinds, revolutionizing computing and drawing on less of our planet's resources. To find out more about Project ACAN, visit our website.
Okay. So, let's look very briefly at a few key facts and questions. First of all, I would like to highlight again that this is ideally suited for artificial neural networks. This has to do with the parallelism of computation inherent in a neural network. If you want more information, you can talk to me about the details later on. We are getting up to 90% power reduction versus like-for-like non-adiabatic circuits, which is actually pretty good, I would say, given the landscape of circuit optimization techniques. Promise this is the only graph that I'm going to show. You see here the power dissipation in white of a non-adiabatic system. This is it working at full blast, and this is when there's no input and it's basically sitting there leaking power. And then we have, similarly with solid and dashed lines, two different versions of adiabatic systems. As time goes on, we are pushing this lower and lower and lower. What does this mean in practice from, let's say, an engineering perspective? It means that 100 nanometer CMOS starts to look like 65 in terms of power dissipation. And if you consider the difference in cost between 180 and 65 cost per square millimeter, cost of design, simply because of the design complexity, and the cost of actually the fabs, the fabrication facilities, this is quite important. We are currently working on a proof of concept demonstrator, 180 nanometer technology, so watch this space. And then the questions we are still answering are how well do these techniques downscale to 22 nanometers and below? We have no reason to believe that they won't, but until we do it, we want to be careful with what we say. And what is the actual saving in a full-size end-to-end ANN that does something? And we are working on one in image processing. So again, watch this space. A bit more now about AI hardware in your business. Just to make a point that whatever business you are in, guests from industry, whether it is for image processing for autonomous vehicles or for making industrial robots and processes more efficient, cybersecurity, where AI is playing an increasingly large role in both attack and defense, natural language processing, need I say more than ChatGPT, and data mining, which allows you in general to make more sense of your data. AI is probably already impacting your businesses in a big way, and it will only continue to do so more. But the important thing is that at the end of every line sits a piece of hardware somewhere in a server, either here or abroad in your business or in someone else's, which dissipates power, requires maintenance, and it has this whole sort of business going behind it, and eventually propagates costs down the chain. That's why it is important that we get hardware right. With that, I would like to thank you for your attention. Feel free to take a picture of my sort of business card slide. Thanks, everyone.